Hi everybody, I'm Giulia Corniani and I'm a PhD student at the Active Touch Laboratory of the University of Sheffield. The study I'm presenting today is about the encoding of stimulus information in the population of tactile afferents. The focus in particular is on tactile afferents innervating the glabrous skin of the human hand, which can be classified into three different classes. Historically, these three classes of afferents have been considered functionally segregated, meaning that every class of afferent is thought to stream unique information toward the cortex. This view grew in light of what we can actually measure from tactile afferents. Indeed, electrophysiology acquisition presents some limitations, as for example, it allows acquiring the activity of just few afferents at a time, while the afferents found on the human hand are approximately 70,000. However, there is growing evidence that challenges this view. Indeed, while each afferent type has specific firing properties and respond to a different aspect of skin deformation, natural tactile stimuli are complex and then elicit the activation of all afferent classes together and simultaneously. Our work investigates the interplay of the three afferent classes when encoding different stimuli features. In particular, we try to move from the classical approach of considering a multitude of single afferents to consider the population of afferents as a whole. Then we look into how the information is spread and shared among the three classes which compose our population. To overcome the impossibility of measuring the whole population of afferents simultaneously, we use Touchsim. Touchsim is a simulator of the spiking activity of human tactile afferents with millisecond precision. With this simulator, we generated the activity of afferents distributed over a line to understand the role of populations regardless of the shape of the end. Our stimulation consisted of a circle indented in the origin of the line. We varied four features, which are the ramp length, the ramp indentation, the frequency of the sinusoid, and the circle radius. We obtained a spike train for each afferent in the population. Considering that we are dealing with populations with thousands of afferents, the first step of the analysis is a dimensionality reduction. In particular, we use non-negative matrix factorization, which linearly decomposes spike trains into non-negative basis function and activation coefficients. We choose this dimensionality reduction method because the non-negative constraint makes the extracted basis function still interpretable as firing patterns. Then we use the activation coefficient obtained for each trial to feed a multinomial logistic regression classifier to decode different stimulus features separately. The output of the classifier gives for each trial the probability of each stimulus feature taking one of the possible values. Those probabilities were then used to compute the information content of the afferent population regarding every stimulus feature. In this way, we can take into account not only whether we can recall the stimulus features from the spiking activity, but also how likely each stimulus feature is. Using our classifier, we compute the information content of each afferent class individually and combining two or three classes together. Indeed, the dotted lines in the radar plots correspond to the information content of the combination of three classes together. For each afferent class, we took the density of afferents corresponding to the one found on fingers of the human hand. What is worth noticing from this plot is that, in general, when considering a combination of afferent classes, we can recall more information content regarding all stimulus features rather than when considering the single classes separately. Then we also explored an upper and a lower bound for the afferent density. For the upper bound, we consider all populations having a density of 140 afferents per square millimeter, while for the lower bound, all populations had 1 afferent per square millimeter. Notice that in this case, the information content is normalized column-wise. Again, in all three cases, considering a combination of classes rather than single classes, we found higher information content regarding stimulus features. However, what is interesting here is that the information content increased dramatically going from the lower bound to finger densities, but this is no more true when going from finger densities to the upper bound. This result might indicate that the combination of afferent densities found on the human hand is somehow optimized for encoding tactile stimuli. Finally, we split the information content of each afferent class into unique and redundant components. We found that all the population contributed with some unique information content in encoding all the stimulus features considered. We explored this split at the lower bound and at the finger densities. Notably, we found that a larger portion of information is unique when considering a lower number of afferents. Still, the redundancy component of information found for real densities might play a fundamental role in the stimulus encoding, accounting in particular for the robustness of the coding, but this point would need further discussions. To sum up, in this work we use a large-scale neural simulator to investigate the stimulus encoding by tactile afferents from a population perspective. We know that afferents belonging to different classes work simultaneously during tactile stimulus encoding, but the traditional belief is that they are segregated and bring complementary information. We found in general that each class carries non-negligible unique information about the stimulus features analyzed. Consequently, the decoder performances improved when considering more than one population concurrently. So our results point towards a sub-modality convergence in the stimulus encoding process. What I show you today is just a part of a more comprehensive work that we are carrying out. We have more exciting results to show coming from the study of tactile afferents on a population level. So keep an eye out for more material, which hopefully will be published soon. Finally, let me thank my colleague Miguel, our supervisors Hannes and Stefano, but also New Touch, the Mercury Innovative Training Network, which is supporting our work. If you have any questions or curiosity, do not hesitate to reach us. Thank you for listening and enjoy Neuromatch.